Hi, it's Phil from My Math Teacher is Terrible. Thanks for joining today. Today I have an interesting problem. One problem that can be solved two ways. The problem as stated or positioned to a student of mine who's a calculus student is use calculus to solve the following equation. 5 to the 6x equals 8320. If you're in calculus, you probably have taken Algebra 2 and have studied sort of the power of using logarithms, and you actually know how to solve this equation without calculus. So I'm actually going to solve it both ways, first without calculus, then with calculus. And then we'll compare our answers. Okay, so let's give it a try. So this is the original equation, and I'm actually going to go ahead and solve it. We know straight away that to get access to this variable, to get access to the x here, we have to take the log of both sides straight away in order to use the properties of logarithms to gain access to this variable. Okay, so let's just take the log of both sides, and we see that, and I'll use ln because I'm a calculus person, but we could use log, it doesn't really matter. You also know that about taking logarithms. Recall that and maybe revisit that on your own. Okay, so I'm going to take the ln on both sides. So I have ln of 5 to the 6x equals ln of 8320. And we know the reason that we do this is because we have the power rule for logarithms, which is that this power comes out in front. So we can rewrite this equation as 6x times ln 5 equals ln of 8320. Now I can do some stuff because I can divide and get this x by itself. When I do problems like this, I tend to leave all of the terms like ln 8320 and ln 5, etc., just like that. And really, as I'm solving, I keep in mind that ln 5 is just some number, so I could divide by it. ln of 8320 is just some number, and I'm really aiming to get some sort of thing where it says x equals whatever so that I can just put it in the calculator and not be subject to any rounding errors. And that's going to be really important in this one. When we do the calculus version, we're also going to be approximating, and we're going to compare the two approximations to each other. But here I know I can simply divide by 6 ln 5. Right, that's just some number. And divide this by 6 ln 5. And the 6 and the ln 5s will cancel, and I get that x equals ln 8320 over 6 ln 5. Okay, and now I'm just going to take my calculator and find out what the heck that is. All right, so ln of 8320 divided by 6 ln 5. All right, and the answer in the calculator is 0.934738. And actually, I have to draw the squiggly equal signs because that's an approximation. But I approximated it to 6 digits. And we're done. That pretty much is it. So when I put this number in here, it's basically 1, but it's really weird because if I put 1 in here, 5 to the 6 is a lot bigger than 8320. We're going to find out when we do the calculus version in a second. But here it is. It's just a little bit less than 1. Done. Pretty straightforward. Again, everybody who's taken Algebra 2 knows that, and if you're taking calculus, you certainly know this. I hope you do. Okay, so now we are going to actually do the calculus version. So I wrote this number down earlier on a piece of paper where I can actually reference it as we go. So I am going to erase this, and then we'll see how we do the calculus version. And the calculus version is going to be an approximation. And when we talk about approximations using calculus, we usually talk about differentials, or we talk about the equation of the tangent line. And that's exactly what we're going to use here. So let's get started. I'm going to erase the blue solution. I wrote this number down. You should too, and then we'll compare. Okay, so we're going to actually remind ourselves about how we use calculus and in finding the equation of the tangent line. So I'm going to just write that up here to remind ourselves. And we want to find the equation of the tangent line at any point xy that's on a curve of y equals f of x, we use the point-slope formula. And for calculus, it has a special form, and you will recall why. Okay, it's y minus y1 equals f prime of x1 times x minus x1. That is, we are given x1, y1. That's our point. And then the slope at x1. We want to know the value of the derivative there because that indicates what the value of the slope is there. Prior to calculus, we just put m in there, right, for slope. But here we have a special form, and that's what we're gonna use here to do our approximation. So, what is f of x in this case? So we do have f of x. F of x is, and I'm going to call it y because it's the same thing. Y equals f of x, which equals 5 to the 6x. All right, and I want to know what value of x produces this y value. So I actually have the y value here. And then all it's going to be missing is going to be the x value. But what the heck is x1, y1? We actually are not given that at all. And if you recall, we usually like to try to get something on the curve of f of x that's actually kind of close to what might produce this answer here. And I said a little bit earlier that 5 to the 6th is pretty big, but actually in terms of an exponential, right, if I'm multiplying the exponent by 6, I mean, this exponential is going to go up really, really fast. And its tangent line slopes are going to go up really, really fast as well. So something that, when I first did this, I was like, oh, but using 1 is not going to be, if I put 1 in here, let's try it. Let's just try 5 to the 6 times 1. What does that equal? Well, it's 5 to the 6th power, really, right? Because 6 times 1. What is 5 to the 6th? 5 to the 6th power is 15,625. Okay, quite a bit larger than this, right? Almost twice the value here. And when I first did the problem, I said to myself, but this is not even close. Like, what would be the point of using something that's not close to this value? But on further examination, I realized that this exponential is going up really fast. And the value between 5 to the 6th and 5 to the 12th, let's say, if I plug in 2 for x, it's gigantic. So this actually is going to be okay. So what does this tell us, actually? So here we did, this really is f of 1, right? Because I put in 1 here, and then I got this value. So really, now I've given myself the point x1, y1. Right? This implies that x1, y1 is 1, 15,625. So I had to create an x1, y1 for myself. And I did. Here's my initial point. And now I'm going to use this point as the point that goes in here, to which I will estimate this value. And some interesting things happen. So let's see, what else? Well, we actually also need the derivative. So let's come over here and calculate our derivative. If f of x is 5 to the 6x, f prime of x, the derivative with respect to x is 6 ln 5 times 5 to the 6x, right? And that is the derivative of an exponential is itself times the ln of the base, and then the chain rule says I have to differentiate the exponent, so that's where the 6 comes from. Okay, so that's f prime of x. And I need f prime of x1, which is 1 in this case. So now let's just put it in here. F prime of x1, oops, let's get my notation looking good. All right. F prime of x1 is 6 ln 5 times 5 to the 6 times 1. Okay, So what do we have? We have 6 ln 5, and as I said earlier, just a number, kind of don't care. And then also this is really 6 times 1 is 6, so this is 6 ln 5 times 5 to the 6th power. All right? So I actually, and then I also know this number, it's 15,625. Super interesting, all right? So now I have all the stuff that I need to go into this thing in order to estimate the number here. And the thing that I want to know is, what's the value of x? This is my actual y value, this guy. I want to find that y value on the tangent line and figure out what the value of x is in that case. All right, so now we can just like substitute all this junk in here and see what happens. All right, so I'm going to say, should I erase? I think I'm going to continue down and see how weird this gets, but okay, y minus y1 is 15,625. This is a terrible looking y. We'll try that again. Okay, y minus y1, 15,625 equals f prime at x1. I calculated this value. 6 ln 5 times 5 to the 6th power. That entire thing is the slope. It's pretty darn big, right? 5 to the 6th times 6. 5 to the 6th is this. That's the value of the slope. Gigantic. Okay. Times x minus x1. What did I give myself as x1? It's just 1. Cool. Okay. And, oh, actually, the y value here. This actually, the y value is this guy. This is my y value. So I have to put this in here, 8320. 8320. Okay, and now we can do a bunch of stuff. Like, I really just want to get all of this away from this, obviously, doing some algebra, so I'm going to just put all of that underneath here. So this is 6 ln 5 times 5 to the 6th. So this is going to go away. This equals x minus 1. Then I'll add 1 to both sides at the end here. But let's just put this entire silly thing in the calculator and see what the number is. Do I want to do that? Yeah, because even if I add 1 and create a fraction, it's still going to be a bit of a nightmare. I could always add 1 to whatever this decimal is, and that's my thinking. Okay, so this mess is going to go in there. Let's see. 8320 minus 15,625. It's minus 7305. And now I'm just going to divide that by this thing. Divided by 6 ln 5. And then 5 to the 6th. Okay. And then I'm going to add 1 to it. This is just algebra. I'm hoping that all of you can really deal with that. Okay, so now I enter that entire expression in the calculator, and now I have the value for x. X equals 0.951586. Okay. Now I've solved that problem using calculus because this x here is what I'm after. This guy. All right, here's my y value on the tangent line. What is my y value? My y value is this, and then what is the x value at that y value on the tangent line? That's it. So I know this guy. I know my y value. I gave myself a y1 of 156.25, and then I also gave myself an x1 value of 1. And all I'm missing is this. And now down here, I have it. Now we can recall what we got earlier from doing the algebra 2 way. That value of x was 0.9347, 38. I mean, these are pretty darn close. They're to 1 decimal place pretty close. And that really is what we're after using this kind of method of approximation. And even taking the ln's and doing it the algebra 2 way, that's also an approximation. And we are done. That's it. So this is the Algebra 2 way on the bottom, and this is the Calculus way on the top by estimating the value of x when we're given a y value on the equation of the tangent line at a particular value. And that really is it. It like goes super quickly once we figure out what's going on. The issue at first blush when I looked at it, I was like, well, dang, I don't have an x1, y1. And again, I thought that these two things were way too far away from each other. But if you plot this exponential, you will see how quickly it goes up. And that's the deal, is that we're kind of relying on it going up super fast. So in exponential terms, something that's 2 times this value actually is negligible, right? For every one of these things, for every one that we increase this exponent, we go up 5-fold. So even that speaks to the negligible nature of something that's twice as much in this case. And that really is the way that this problem is solved. This is the calculus way, and we did the algebra 2 way a little bit earlier. And we see they're pretty darn close. I mean, this is a typical like test question that sort of demands that you do it in a particular way. I'm not sure. It's a toss-up between how I would do it. I think maybe to practice this, I would do it this way, and maybe to practice the algebra 2 way, I would do it that way. Or as I did here, both, and then compared the results. That's all. Super interesting. Very, very interesting. And see if you can't take this approach and use it in other calculus problems. I mean, the big key here is using the point-slope formula for the equation of a tangent line given a point x1, y1. That's the key to this. And then picking an appropriate x1, y1 in the context of the problem. Normally, with a line or a parabola or something like that, this would make no sense. But in the context of an exponential, it does make sense because this exponential is going up 5-fold for every value of x that's going up. Oh, excuse me, for every value of 6x that's going up by 1. Yeah, and that's all. Thanks for joining, and I hope you found this as interesting as I did. And if you have any comments, please leave them in the comments section. Would love to hear from you. If you liked it, if there's something I could change, etc. That would be awesome. And I will be doing some more videos. I'm trying to ramp up my number of calculus videos because that really is my specialty, and I love calculus. So, and I also love talking about interesting problems like this. So stay tuned. If you like the video, click like. If you like the channel so far, please subscribe. Tell your friends about it. Tell your terrible math teacher about it and see if they can't get a little bit better at what they're doing. Also share it with your good math teachers. Again, thanks very much, and I hope to see you next time. Thank you.